Let me begin by saying what this video will be about. If you've come across the term entropy in your career but never really understood what it means, this video is for you. I want you to develop an intuition about what the concept of entropy truly means. Most of this video is about what information is from a mathematics point of view and what entropy is trying to tell us. There is a section on how entropy comes up naturally in the world of AI, but I'd say that is a small part in the end. But if you stick around till the end, you'll probably be able to figure out on your own why is entropy used so widely in the world of AI. So let's get started. Imagine someone pulls out a playing card in front of you, but they don't tell you what it is. Then they tell you it is a red card. So you get some information about the card, but not a lot since half the deck is red. Then they tell you it is a diamond card, and you get more information. Then they tell you it is the highest value card. Assuming you assign the highest value to an ace, you have all the information you need to know which card it is. Notice, as you accumulate information about the hidden card, there is a decrease in how common or how probable that piece of information is. For example, when it was revealed it is a red card, you get some information, and the probability of the card being red was 50%. When you get to know it is a diamond card, you have even more information, and the probability of it being a red and a diamond was 25%. Finally, when you get the last detail, you have all the information you need about the card, and the probability of it being a red and a diamond and an ace was 1 over 52, or 1.92%, which is the lowest it can be in this case. If we observe what is happening here, we see that the more unlikely or improbable an event is, the more information we have from the event. In other words, probability and information have an inverse relationship between them. But this begs us the question, what even is information? Let's dive into this experiment further. If you think about how many possible states there are for a playing card, it's 52. And as we collect more information about the card, the possible number of states the card could be in is reduced. So we start with 52 possible states because the card could be any one out of all the possibilities. We get to know it is a red card, so the possible states the card could be in is reduced to 26. We learn it is a diamond card, the possible states are reduced to 13. We learn it is not a number card, possible states are reduced to 4, that is king, queen, jack, and an ace. We then learn it is either a king or a queen card, possible states are reduced to 2. Then we finally learn it is a queen card, so the possible states are reduced to 1. At this point, since there is just one possible state, we know for certain it is a queen of diamonds. If we think about probability, we should think in terms of ratio of states. So if we think about what the probability of an event is, it is simply the number of states fitting that event description divided by total possible states. For example, for a red card, we know that the number of states fitting the description of red is 26, and the total possible states a card could be in is 52. So the probability of a card being red is 26 over 52. Next, for a diamond card, the number of states fitting the diamond description is 13, and the total possible states is just 26 because we already know it is a red card. So we multiply the probability by 13 over 26. Similarly, for a card which is not a number, the number of states fitting this description would be 4 out of 13. And we keep on updating our probability as we reduce the number of potential states of the card. What I want you to understand from this is that we gain information as we reduce the possible number of states an object can take. You can pause for a second to think about the statement, because this is fundamental to the intuition on how the concepts of probability and information are interconnected. So if we make the statement more precise, we define that we get 1 unit of information when the possible number of states is reduced to exactly half. This definition was invented by someone named Claude Shannon in 1948. So it's sometimes also called the Shannon information. And the unit of information is called bit. And the idea of bits of information being tied to the reduction of states is something that might not make organic sense. So allow me to explain it visually. So let's suppose we have a random variable x which can take a bunch of possible states. And if we consider x being on a continuous spectrum instead of a discrete set, we can use this pink area to represent the possible states of x. Initially, we don't have any information about x, so we can say we have 0 bits of information. And if we think in terms of possible states of x as a fraction, we can say it is 100% or 1, since it can take any of the possible states there are, right? If we go by our definition, we gain 1 bit of information when we reduce the possible number of states to half. Similarly, we get 1 more bit of information when we reduce the number of remaining states to half. And if we repeat this process n times, we say we get n bits of information and the possible states of x have been reduced by half n times. But wait, if we think about the states as a fraction of original, isn't that just what the probability of an outcome of x is? We can denote the probability as p, and if we do some basic algebra, we can see that n bits of information in this case is log base 2 of p. And if we generalize, we arrive at this equation which says information from an event of x is simply equal to log base 2 of probability of that event. And there you go. This mathematical equation is what defines information. And what this means is that if an outcome of x has a probability p, then the information we get when that outcome happens is minus log of p. And if we graph this equation, we get a nice inverse curve. So when the probability of the event is low, the information gained is high. And when the probability is high, the information gained is low. It also quantifies our intuition about information having an inverse relationship with probability, as we mentioned during the start of the video. So to recap, we get 1 bit of information when the possible number of states of a random variable is reduced to half. But there is an assumption here which we haven't discussed. The hidden assumption is that the probability of all states of the random variable should be equally likely. What that means is each state of x should have the same chances of occurring. Consider what happens when this condition is broken. Let's talk about the nice case first. Say we roll a dice having 6 faces and each face has an equal probability of landing. So each face or each state has a probability of 1 by 6 or 0.167 if we round off. Before rolling the dice, the possible number of states our dice can take is 6, since any of the faces could land, right? Now we roll the dice and we get a 4, let's say. We reduced our possible number of states from 6 to 1. So according to our formula for information, we get minus log of 1 by 6, which is 2.58 bits of information. All good so far. But now consider that the dice is rigged and the probability of landing a 4 is much higher, 50% or 0.5. So now the probability of landing each face is not the same anymore. Again, if we assume we land a 4, the number of states technically still go down from 6 to 1. But the information revealed according to our formula is 1 bit. So what is happening here? So if we look closely at the formula for information, all there is on the right hand side is probability. And if we really think about it, what the information formula is saying is that we gain 1 bit of information when the sum of probabilities of the possible states of x is reduced to half. But since this could be a little difficult to remember, I suggest relying on the intuition we have discussed until now, with this assumption in the back of our mind that the probability of each state is equally likely for the intuition to hold. If nothing else, what I want you to get from what we've discussed so far is that the information revealed is inversely related to probability. Lesser the probability of an event happening, more the information is revealed. With the intuition that we have, let's talk about the next topic, entropy. Entropy is one of those names which reveals nothing about the concept until you dig into the explanation itself. If you're familiar with the concept of expectation from the world of probability, we can think of entropy as nothing but expected information gain over all possible states of x. I like to think of expectation as a fancy word for weighted average. So essentially what this formula is doing is taking a weighted average of information for all states of x. Intuitively speaking, what the formula tells us is, on average, how much information do we get when a state of x is revealed? And since we know that information is inversely tied to probability, we can say what entropy asks us is, on average, how improbable is a state of x? And if we really think about what the second statement is, it says, on average, how unpredictable is a state of x? Because think about it, probability is essentially tied to predictability. If we toss a coin, the outcome is quite unpredictable, because the probability of landing a heads is just as much as probability of landing a tails. But if we play a slot machine at a casino, and if we consider possible outcomes as either a win or a loss, we can be almost sure that the outcome would not be a win, because the probability of losing is so much more than winning. In other words, we can say there is little unpredictability in the case of the slot machine. And if we notice, what these probability distributions tell us as unpredictability is high when the probabilities are evenly distributed across the outcomes. If this is confusing, let me share a visual example. Let's say you're playing a certain version of a game of darts. The rectangular area shown in the center is the dartboard, and for the sake of this experiment, let's assume you're bad at the game so your throws can land anywhere on the board. Your goal is to predict which color would the dart land on. Initially, there is only a single color, red. So you can predict with 100% confidence that the dart would land on red. In other words, the unpredictability of choosing the correct color is 0. Now, as we add another color patch to the board, your predictability would go down, right? You'd still bet on red since it occupies the largest area, but there is a small chance it lands on yellow. In other words, you are no longer 100% confident with your prediction, which means there is some unpredictability involved. As we increase the number of color patches, your predictability of choosing the correct color would go down, right? So we can say the predictability or unpredictability would depend on the number of color patches there are. But is that the only factor affecting your predictability? Well, not really, right? We can have unequal proportions of the patches on the board. In this color arrangement, despite the number of colors remaining the same, your predictability would go up since red occupies the largest area out of all colors, which is what you want to bet on. This intuition is essentially what entropy captures. If we think of colors as states of a random variable, entropy measures unpredictability in the system by considering both the number and ratio of states. And if we equate the fraction of area of the color patches to probabilities, entropy simply takes the average information gained from these states. Because remember, information is inversely related to probability. So taking an expectation of information is like taking a weighted average of unpredictability. The higher the entropy, the more unpredictable or random the system is. And if we use our formula, the entropy is lowest when there is a single color or single state, that is 0. Which makes sense because there will be no unpredictability in the system. Whereas the entropy is maximum for a given number of states when the probabilities are evenly distributed across all states. And as the number of states increases, the entropy also increases, which also makes intuitive sense, right? Because there will be more outcomes to choose from, which means higher unpredictability. And this brings us to our next section. Why does AI rely on entropy? If you followed closely this far, I bet you can already predict the answer to the question, why does an AI model rely on the concept of entropy? But before diving in, let's see what a probability distribution looks like for different extremes of entropy. If you assume that some random variable x has 7 equally likely states, its probability distribution will look something like this. Probability shown on the y-axis and the states on the x-axis. Since each state is equally likely, the probabilities are evenly distributed, and the graph is horizontal and flat. And if we use this little yellow pointer to indicate our variable x taking a state, changing with time, you will see that it will randomly shift between all states of x. Based on what we've learned about entropy, we can say predictability is low or unpredictability is high in this case. Whereas if we look at a probability distribution where some states are much more likely than others, our yellow pointer will mostly point towards the highly likely states, in this case 2 and 3. So we can say that here the unpredictability is low. So what does it have to do with AI? Well, in the end, AI models are usually predictive machines, and their predictability is modeled using a probability distribution. Take an example of an AI model which tries to predict which animal an input image is. For simplicity, let's assume the model is a neural network, with its last layer of neurons having a 1:1 mapping to a predefined set of labels. I'm not going to go into how a neural network works, but for our case, we can assume that our neural network produces a probability value for each label, which indicates how likely is our input image defined by that label. So in this case, our AI model is predicting the chances of the photo being of a pig at 4.9%, a wolf at 25.1%, and so on. In a simplified version of a neural network, the label with the maximum probability value is chosen as the final output. In this case, the label dog has the highest value, so it will be chosen as the final output. But do you think we should only be concerned with the maximum probability value? Consider a case where probabilities are almost equal, with dog still having the highest value, but only slightly higher than others. Technically, this will also lead to the final output being dog, but can we really trust AI's decision? Well, not really, right? Given the probability for dog is only slightly higher, we won't feel as confident in the AI model's answer. As a real-world analogy, if a medical report says there is a 6 on 10 chance you have disease A versus another report which says there is a 9 on 10 chance you have disease B, it makes more sense to go with the second diagnosis because the prediction score is higher. Similarly, here, we would want our neural networks to exhibit high predictability, that is low unpredictability or low entropy. And this is why we use entropy while measuring the performance of an AI model's output, as it helps us quantify the unpredictability exhibited by the model overall. In this case, we can exactly quantify the unpredictability by calculating the entropy of our probability distribution, which comes out to be 2.689. Whereas if we calculate the entropy of the previous case, it comes out to be 1.748, which is a better result. AI models should strive to minimize the entropy of the probabilities they produce because it kind of mimics a confidence score of the model. The more confident a model is with its predictions, the more trustworthy it is. And there you go. This is why entropy comes up at multiple places when we work with AI models. To be more precise, the models usually rely on a metric called cross entropy or KL divergence. But the underlying principle remains rooted in what we just talked about. So, in summary, information is gained when we reduce the number of states of a variable. It is inversely related to the probability of an event, whereas entropy measures, on average, how much information do we gain from the states of X. Intuitively speaking, it is also a measure of unpredictability in the system. I hope you now have a stronger understanding of what the concepts of information and entropy are. If you do, please like this video and let me know in the comments what other topics you would like to learn in the future.